Come and see me for once. You don't ever come to me. You don't ever come to me. All she hit me with is come and see me for once. Come and see me for once. Oh, y'all never come to me. Y'all never come to me. Why you gotta start, girl? Why you gotta start? I know we make time for the things that we want. I know you got another nigga trying to play the part. So cause you got a heart, don't mean he got a heart. Could be standing in the field and he still ain't in the field. If anything should change, then I thought we had a deal. Lately you keep questioning what you get out the deal. Doing things that make me feel the way I make it feel. How hard is it to let you know when I'm coming home?
Thanks for the gifts, babe.
That way you could be prepared. Maybe take a couple sick days and not miss pay. I don't even know what things are looking like inside of your place. How it's decorated. This thing is getting one-sided. I can't even lie to you right now. Yeah. All she talking about is come and see me for once. Come and see me for once. Y'all never come to me. Y'all never come to me. Yeah. All she hit me with is come and see me for once. Come and see me for once. You don't ever come to me. Y'all never come to me.
He really said any day now. I thought when I wear black, I look skinny. I think I have body dysmorphia.
Whoa. Shawty, you better she
I mean, the
belong to
chicken
me.
bacon
She
ranch
got
sub.
fatty, I'm paying the lease. Bought in the jet and we going to Greece. We having sex on the boat on the beach. Took off the top so you... I might be too strung out on compliments, overdosed on confidence, started not to give a fuck and stop fearing the consequence, drinking every night because we drink some of my accomplishments, faded way too long, I'm floating in and out of consciousness and they saying I'm back, I'd agree with that, I just take my time with all this shit, I still believe in that, I had someone tell me I fell off, ooh I needed that, and they wanna see me pick back up, well where'd I leave it at, I know I exaggerated things, now I got it like that, tuck my napkin in my shirt cause I'm just mobbing like that. You know good and well that you don't want a problem like that. You gon' make someone around me catch a body like that. No, don't do it. Please don't do it. Cause one of us goes in and we all go through it. And Drizzy got the money, so Drizzy gon' pay it. Those my brothers, I ain't even gotta say it. That's just something they know. They know, they know, they know, they know. They know, they know, they know. They know, they know, they know. Yeah, they know, yeah. That the real is on the rise. Fuck them other guys. I even gave them a chance to decide. Now it's something they know. They know, they know, they know. Yeah, I be yelling out money over everything, money on my mind. Then she wanna ask when it got so empty. Tell her I apologize, happened over time. She says they miss the old Drake, girl, don't tempt me. If they don't get it, they'll be over you. That new shit that you got is overdue. You better do what you're supposed to do. I'm like, why I gotta be all that? But still I can't deny the fact that it's true. Listen to you expressing all them feelings. Soap opera rappers, all these niggas sound like all my children. And that's who you thinking is about to come and make a killing. I guess it really is just me, myself, and all my millions. You know that they ain't even got it like that. You gon' hype me up and make me catch a body like that. Cause I live for this, it isn't just a hobby like that. When they get my shit and play it, I ain't even gotta say it, they know. They know, they know, they know, they know. They know, they know, they know. They know, they know, they know. Yeah, they know, yeah. That the real is on the rise. Fuck them other guys. I even gave them a chance to decide. Now it's something they know. They know, they know, they know. I be yelling now, money over everything. Money on my. Tell them I apologize. It happened all the time. Time. They know.
You hear that? That's not just a Toyota truck. That's the sound of no crowds, no alerts, no distractions, and no telling what you'll find next. You know, like a detour. So why would you ever take a tour when you could take a detour? Toyota trucks.
Yeah. The problem is I just went in Tropical Smoothie and picked up my order. And that man said, any day now. Which means I must look really huge. And it hurt my feelings. Because what would make you say any day now? That's not funny. That's not funny. That's not funny.
And I be there soon as I make it home. And she a patient in my waiting room. Never pay attention to the rumors and what they assume. And until them girls prove it, I'm the one that never get confused with. Baby, you my everything. You all I ever wanted. We could do it real big, bigger than you ever done it. You be up on everything. Other hoes ain't never on it. I want this forever. I swear I could spend whatever on it. Cause she hold me down every time I hit up. When I get right, I promise that we gon' live it up. She made me beg for it till she give it up. And I say the same thing every single time. I say you the fucking best. You the fucking best. You the fucking best. You the fucking best. You the best I ever had. Best I ever had. Best I ever had. Best I ever had. I say you the
Yo, you the only one that see the real Nikki. I can show you chill, Nikki, cause of how you deal with me. When they knock my blocks down, you come and you build with me. Even though you real busy, you the fucking real drizzy. It's so amazing. I figured out this world is ours for the taking. I figured out that when I go out and those people scream, that some of them are living vicariously through me. That's why I put that S on my chest and I'm corn. But on another note, let's have sex in my dorm. And I'ma make you beg cause you look pretty when you begging. So meet me on the campus, I'll be there around 11. And let me put my books down. Excuse me if I look down. Guess I'm a little nervous, but I bet you serve it. Look at what you took Baby, you're my everything. You're all I ever wanted. We can do it real big. Bigger than you ever done it. We'll be up on everything. I can make this never own it. I want this forever. I swear I can spend whatever on it. That's why I hold you down every time you hit me up. When I get right up on it, that we gon' live it up. I make you beg for it until I give it up. You say the same thing every single time.
You the fucking best. You the fucking best. You the fucking best. You the fucking best. You the best I ever had. Best I ever had. Best I ever had. Best I ever had. I said you the fucking sex, love, pain, baby. I be on that tank shit. Buzz so big, I could probably sell a blank this. When my album drop, bitches will buy it for the picture, and niggas will buy it too and claim they got it for they sister. Magazine, paper, girl, but money ain't the issue. They bring dinner to my room and ask me to initial. She call me the referee cause I be so official. My shirt ain't got no stripes, but I can make your pussy whistle. Like the Andy Griffith theme song. And who told you to put them jeans on? Double cup love, you the one I lean on. Feeling for a fix, then you should really get your fiend on. Yeah, just know my condo is the crack spot. Every single show she out there repping like a mascot. Get it from the back and make your fucking bra strap pop. All up in your slot till a nigga hit the jackpot. Baby, you my everything. You all I ever wanted. We could do it real big. Bigger than you ever done it. You be up on everything. Other hoes ain't never own it. I want this forever. I swear I could spend whatever on it. Cause she hold me down every time I hit up. When I get right, I promise that we gon' live it up. She made me beg for it till she give it up. And I say the same thing every single time. I say you the fucking best. You the fucking best. You the fucking best. You the fucking best. You the best I ever had. Best I ever had. Best I ever had. Best I ever had. I say you the fucking best. You the fucking best. You the fucking best. You the fucking best. You the best I ever had. Best I ever had. Best I ever had. Best I ever had. Oh yeah. See, this is the type of joint you gotta dedicate to somebody. Just make sure they that special somebody. Young Money. Yeah. Yeah. Hey.
I wanna soldier.
Where you got?
A BetterHelp ad. October 10th is World Mental Health Day, and this year, youth therapists behind every supportive moment and small win is a therapist who showed up and made a difference. BetterHelp has supported over 5 million people globally on their mental health journeys. With 12 plus years experience in the world's largest online network of qualified therapists, it's easy to match with the one that's right for you. See for yourself. Visit BetterHelp.com/explain for 10% on the first.
I don't wanna give you the wrong impression. I need love and affection. And I hope I'm not sounding too desperate. I need love and affection. Love, 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 love and affection. Love.
Oh my gosh, this is the best lane. Come on! Oh, I'm gonna get to this thing.
Oh, baby. I'm not asking for the world, maybe. You can give me what I want, baby.
Oh, hell no.
Come home tired and when I'm drowning, save me. Give it to me on a daily. If I'm your girl, say my name, boy. Let me know I'm in control. We both grown, so how we feel, we can let it show. I won't play around. I wanna lay you down. I need you now. I need you now. Oh.
I don't wanna give you the wrong impression. I need love and affection. And I hope I'm not sounding too desperate. I need love and affection. Love, love, love and affection. Love, love.
Boy, lately, you've been stingy with your time. Got me wondering, I'm wondering if I'm on your mind. Boy, I just wanna be in your possession. Say I'm the one you want, so come express it. Don't slip, cause a nigga might push up on it. Don't really wanna lose this moment. While window shopping, you on this side. Don't put it down, don't fuck around. I want you now, oh.
I don't wanna give you the wrong impression. I need love and affection. And I hope I'm not sounding too desperate. I need love and affection. Love, I'm too desperate. I need love and affection. Love, affection. Love, affection. Love, L-O-V-E, affection. Can't get love me for poor. Let me know. I'm searching for my soul. Rockstar. Whoever turned you cold. You need to let it know. Yeah, I can work miracles. What's up? I work your physical. Turn up. And when I love you close, you can feel my heart beating through the clothes. I don't wanna give you the wrong impression. I need love and affection. And I hope I'm not sounding too desperate. I need love and affection. Love, love and affection. Love, L-O-V-E, affection.
So buy a zip of weed, hit the club, pay for about 10 niggas to get in. We crunk, lit, any bitch. Yeah.
No, we walk around the world, stepping out, giving a damn by where our feet land at. Yeah. Get your ass mushed, smushed. Yeah. 21. The biggest. Put a nigga in the chicken wing. Pussy.
21, can you do something for me?
21.
Can you hit a little rich flex for me?
21.
Then 21, can you do something for me?
21.
Drop some bars to my pussy ex for me. Then 21, can you do something for me? Can you talk to the ops next for me?
Okay.
21, do your thing, 21, do your thing.
21.
Do your thing, 2021, do your thing.
21.
Do your thing, 21, do
Yellow
your
diamonds
thing.
in the watch. This shit costs a lot. Never send a bitch or die. That's how you get shot.
They're non-homogeneous, so they're not going to be equal to 0 on one side of the equation. They'll get lots more prefixes. Kind of the thing that I kind of want to impress upon you is that we are taking a look at a very particular slice of differential equations when it comes to the act of actually solving differential equations in this class. That's sort of the impression that I kind of want to leave. We're not solving, we're not even getting close to even broaching the topic of solving all such differential equations. Just one particular category. Okay? Alright. There is one kind of thing that is pretty typical when it comes to the theory of differential equations. And it's usually our very first stop on sort of our, trip through solving differential equations. And that is slope fields. They have other names. Some of those names that I'm aware of are like phase planes or phase portraits. Other things, actually, you know what? I don't think I can think of any other names that I've heard for this particular thing other than slope fields, phase planes, or phase portraits. And this is the idea that if we have a differential equation, then we can rely on our understanding and intuition of what it means for something to be a derivative. This is a quiz time, a review of Calc 1. So exciting, right, Braylon? What is one of your fundamental interpretations of what a derivative is?
The slope of the tangent line.
Slope of the tangent line. The other one being
Instantaneous rate of change.
yeah, I rock.
You do.
So do you.
Oh, thank you. It's very kind of you to say.
So if we're interpreting dy dx as a slope of a tangent line, a literal slope, then the idea is if I look at a plane, all of the individual points on this plane are made up of an x-coordinate and a y-coordinate. And what I can do is I can plug in each of the points x and y coordinates into my differential equation and get whatever the slope of that particular tangent line needs to be at that point. So if I plug in, say, -1, 1 into here, I plug in -1 in for x, I plug in 1 for y, I get dy dx is equal to 1. I know the slope of the tangent line to any curve that follows this differential equation at that point. It's got to be 1. So I know the slope's kind of like that. And I do that for every point. So I can plug it in at 0, 1, 1, 1. I can plug it in at -1, 0, in which case my slope is 0, so it's horizontal here. Slope here is 2, so it's slightly steeper. Slope up here is 3, so it's slightly steeper still. And the collection of all of these points and all of their slopes in a particular window of interest is our slope field or our phase plane or our phase portrait, whatever words you want to use to describe this particular thing. Math people tend to say slope fields. I have heard phase portraits from electrical engineers. And I have heard phase planes from a math book. So.
What was the slope field, slope plane, slope portraits again? Could you say it again?
This thing, the collection of all of these
Collection
planes
of them all.
and their slopes. Typically when it comes to slope fields in actual application, we're usually using computers to generate these slope fields to look at. But because you all are Calc 2 students, you all get that joy of sketching and drawing your own slope fields. Plug in some numbers, you get a slope. You approximate how steep it needs to be based on that slope. like how I walked away and then suddenly this isn't working. Oh, that's why it's not working, is that fast. So this is a phase portrait of my differential equation. dy dx is equal to y. And with the exception of drawing this via hand drawing graphs, I cheated and used nice computer graphics. This is Desmos. I programmed this. So you know it's got to be good. It's not good. This has the title First Attempt at a Slope Field, because this was the only way I could make Desmos make it work, and not because it was a good way. So we're kind of seeing from our little slope field here all these different slopes, and if you imagine for a second, like in your heart, could you imagine a particular, what's the word I'm looking for? An exponential function kind of shape. E to the x. You kind of imagine that, Diego? Maybe a little bit. It's kind of visually cluttered, but you can kind of see. Here's our exponential function, and it's kind of going along these various different slope lines. And this is where we get into some more words here. Those words being the general solution to a differential equation and a particular solution to a differential equation. The general solution, at least for this particular phase portrait, is sort of represented by kind of the phase portrait itself. It is the collection of all functions that you can imagine or that you could fit into this phase portrait. It is the collection of all functions that solve the differential equation. And then a particular solution would be something like e to the x here. It is one solution, just a curve. It doesn't need to be the most general solution. It doesn't even need to have particular kind of qualities. It just needs to be one solution, just one curve. There is another particular solution, and I am using the word particular in the mathematical sense of it is a curve which fits the slope field, which you can see and kind of identify here, which is very clearly not exponential. So look at the slope field with your eyes. And find, some kind of curve that passes vertical lines. That's got to be a function, which lies on the slope field. What you thinking, Richard?
I was gonna say parallel with or on the x-axis.
Yeah, this parallel line here.
Slope is 0.
Slope is 0. And that would certainly fit and solve this particular differential equation. If I plugged in 0 in for y, what's the derivative of 0? 0, and 0 is equal to 0, I hope. So the function 0 would actually solve this differential equation, where no other constant would. And it is represented on this particular slope field by this green horizontal line that's going through the x-axis. I'm sort of running out of space here, so I'm going to go over to the right. And this is where my spelling skills will fail me. Equilibria. Sorry?
I thought you were trying to spell equilibrium.
No, equilibria. It is the plural for equilibrium. So an equilibria is a particular solution to a differential equation which has a constant slope of 0.
Equilibria is plural, and you should say are particular solutions.
That sounds too Englishy for me. I'm going to stick with what I have because it's more genuine and mistake-filled. Who knows anything about grammar? It's all made-up rules anyway. So we have here an equilibrium or an equilibria. It is at a y-coordinate of 0, so it's the line y equals 0. And there are two different kinds of equilibria, and this is why I have that little yardstick or meter stick over there. There is the difference between an unstable equilibria and a stable equilibria. One of the many differential equations that people have studied over the years, and we have in the past maybe 30 to 40 years finally solved exactly, so without any numerical computations going on at the very actual analytic solution. It's only taken maybe 500 years. Is the behavior of a pendulum. There are various different kinds of approximations that we can make for the motion of a pendulum, which could make solving a differential equation which models its behavior, its motion, easier. The most common one is the small angle approximation. It's kind of pretty easy to solve a differential equation in the approximation that we don't actually start the pendulum from very high. Once we start the pendulum from very high, then it becomes way more difficult. That approximation even fails. But as I swing this pendulum, there is a position, a spot, where the pendulum is naturally gravitating towards, and I was saying gravitate towards in the ironic sense of literal gravity, right around there. And it doesn't matter how I perturb this particular system, it will always tend towards that particular spot. And here's a question, Blake, when it's in this particular spot, what would you say its motion is? Nothing, or 0 mathematically, right? Which matches up for our notion of what an equilibrium or an equilibrium is. So because all of these various different starting places tend towards this particular equilibria, we would call this a stable equilibrium. Which does bring up what the next one is, unstable, which would be a little bit something like this. Now, if I were you know, perfect in every way, I could get this thing to stand up perfectly. And again, if I were perfect and this thing were perfectly balanced, what would its motion be like? Zero. So it would also be in equilibrium, but any perturbation, any change to that perfect initial condition and the solution, the motion tends to go away from that equilibrium. That would make this thing an unstable equilibrium. It is an unstable structure. So here we have an equilibrium. I have here a solution curve, a particular solution for e to the x. And as I am reading this in the usual math way of lexicographically, left to right, this solution of e to the x, is it tending away from our green equilibrium, or is it tending towards our green equilibrium?
Going from left to right away.
Yeah, left to right. We always read left to right. It's going away. So if you were to ask to classify this equilibria of y equals 0, you would say that this is an unstable equilibrium. Okay? Typically speaking, these kinds of slope fields and these kinds of differential equations have came up with, or came around because of population modeling. Thomas Malthus is probably the person who is the most well-known example of somebody in history who tackled the problem of population modeling, and will be remembered in history as the person who did it first and did it the worst. Because he said this is how your population is going to grow. They're going to grow with a constant multiple of themselves. And he was kind of making this observation based on the fact that, if we have a population, that population reproduces within that population. So there's some proportion of that population which is causing reproduction. So it's not a crazy, wild, out there kind of way of modeling population, which is why Malthus is kind of remembered for that. But it's also just so bad, like populations don't explode off exponentially. A slightly better population model would be if we had some kind of other term or factor which prohibited our growth. Let me make this a little flatter. Here we go. So suppose super hypothetical situation. We have a population model here, and our maximum theoretical population we're saying is 5. Right, so what we're observing here now, instead of that Malthusian exponential growth, is my particular solution curves are going to come up here, follow this, go up, but at a certain point, say as the population reaches the sort of natural resource maximum of their particular environment, the population's growth starts to drop off asymptotically as we approach that theoretical maximum. So it's a little bit of a better population model. It also works very nice as a question of, hey, where are equilibria here? What do you think, Diego? Where are equilibria here? 0 and 5. Which of them is stable, which of them is unstable? Or are they both stable or unstable?
Unstable would be 0 and 5.
Yep, we're leading left to right. If I read left to right, all these potential solution curves I can imagine on the slope field are all going away from 0. If I read left to right, all these potential solution curves I can imagine on the slope field are all going away from 0. which would mean 0 would be unstable. And all of these solution curves that I'm imagining are going towards 5. So 5 would be our stable equilibrium.
What about the ones on top of the 5?
This would be in a scenario where like our population is larger than what that environment can sustain. And so we kind of are in a position where unfortunately people are gonna die. And so our population is going to fall and still approach that stable equilibrium. Still approach a theoretical maximum that this particular environment could sustain. Okay. These are pretty typically going to be the first kinds of problems that you will be asked to do, and this is where I wish that projector wasn't so high or aimed so high. The first kinds of problems that you might be asked on a quiz or an exam or something would be, here is the slope field. What are your equilibria? Classify them. And then sketch a particular solution through some point. So I'm gonna hope your glare isn't too bad. And let's pretend for a moment that the instructions for this particular problem are sketch the particular solution containing 1, 2. X equals 1, y equals 2. So I'm gonna go over here to my graph, find the point 1, 2. And what I'm going to do is I'm going to try and sketch the function coming from that particular point, following the slope fields in both directions. So my slope field here is kind of steep, so I'm going to make my graph kind of steep. And then I need it to kind of fall off a little bit as we go up to our equilibria. No, I'm not going to draw on the wall. I don't want facilities to yell at me. But then my particular solution would be curving asymptotically over to the right. And then as I go over to the left, I'm kind of coming down a little bit, trying to match those particular slopes. Stay. So just imagine like I actually drew off the board and up top in the asymptotic approach at equilibrium. Emma, where are equilibria here?
-1 and 3.
-1 and 3. Perfect. Sophia, which ones are stable, which ones are unstable?
Stable would be -1.
Okay.
And unstable would be 3.
Okay. And I would agree with that, right? If we're at 3 and I'm kind of imagining a solution curve, I'm going away from 3, either up top or down below. Hoang. Catch. Draw your solution curve. Draw your particular solution containing the points. Let's do 2, 1. Okay. I would not have taken points off. This is a nitpick. But I would have liked to have seen the full asymptotic behavior going in both directions. But again, that's just being a nitpicker. I would not take off points for that. You got the general principle. Zach, give me one equilibrium.
Negative 1/2.
All right, Blake, give me another equilibrium.
1.
All right, Brandon, give me our last equilibrium. 6. Gavin, what are my stable equilibria?
1.
That's it. Solomon, what are our unstable equilibria?
Negative 1/2 and 6.
Gavin. Not Gavin, sorry. I was looking at the wrong person. Diego. Catch. Draw a particular solution through 0, 5.
Can I write the word?
Oh, I'm stupid.
Let's stack a bunch of desks and I'll climb up there. I volunteer.
You're not writing on the walls either.
We can move the thing down the projector, I believe.
Yeah, I'm not getting facilities mad at me. And I'm certainly not getting the team of students mad at me for, either risking my or a student's life.
What if I volunteer?
No.
Then I'm the one that's risking.
No. Absolutely not.
We'll send you out of the rooms, then you know.
Right, well, he's saying no, but if you go and do it, he's not gonna go and tackle you to stop you, so. He just has to say no for his own,
Yeah, that'll be assault. I'm not gonna assault a student.
oh,
How are we doing? Okay. It's time where I give you a problem. I'm gonna give you a dastardly and devious differential equation to solve. Or not really to solve, but to work with. Actually, no. Here we go. What I want you to do is I want you to sketch the slope field. for whole numbers in between, we'll say -3 and +3. Let's not go too crazy here. And y coordinates whole numbers between -3 and +3. Again, let's not go too crazy here. And then I want you to sketch the particular solution containing the point -1, -2. Alright, so your slope field should hopefully look a little something kind of like this. A little something like this, Gavin? Alright, -1, -2 is the place where we want our particular solution. So that looks like, what, right there-ish? So my particular solution, if I go backwards, kind of looks like it goes up a little bit, and then potentially starts following this particular line up here. And if I go the other direction, it just goes down. There is a particular kind of straight-ish diagonal line that's kind of going down with a constant slope of -1. Can you kind of see that look? Fancy word that I don't super care about, but some people care about. This is what's called an isocline. Iso being same, and I have no idea where cline comes from. Probably German. But an isocline is sort of related to an equilibrium. It's a generalization of an equilibrium. It's just a curve on a slope field where the derivative happens to be constant on that curve. So no longer a straight horizontal line like an equilibrium could be any kind of curve, and no longer derivative equal to 0 like equilibrium could be any derivative, as long as it's constant along that curve. And sort of the idea behind isoclines is they're meant to partition a slope field in the same way that equilibria do, but just not in as nice of a way. Which is why I don't super care about isoclines. It's something, I guess, to be aware of. Okay?
Okay, I got a question.
Okay.
So it's no equilibrious.
Not for this one, no. No
Okay.
equilibria here.
So it's just going to be a straight line.
What do you mean?
Like straight, like when you point it up towards up there, it's just going to be like straight.
It's not going to be like, like when you're up here.
Yeah.
Yeah, our solution curve is going to approach this kind of straightish line up here. But as we go to the right, this thing's going to shoot down.
Okay.
No equilibria, there is an isocline, but you just still follow the shape of the curve. A slightly more interesting solution curve would be the solution curve at 0, 0. Right, this solution curve containing that point. And I say it's slightly more interesting because it's not going to be like sort of just a decreasing line here. This is where I wish, again, this was lower. You're not allowed to climb up. If I imagine for a second my particular solution here going to the right, as I move to the right, all my slopes have started pointing up. So my particular solution here has kind of got to turn around and start going straight up. Whereas if I go in the other direction, I'm going to start approaching that diagonal line and start going along that diagonal line. So you have sort of a weird kind of interesting particular solution. We come down sort of asymptotically, we hit 0, 0, and we turn straight around and start heading back up. Well, just one of those kinds of interesting things. I would say the behavior up here is just a little bit more interesting than our behavior down here. Doing all right, Zach?
Yep.
All right. Because our next problem type is now coming up. Verify, or I suppose unverify, whether or not the following is a solution to the differential equation. So we got something like y equals sine of x minus cosine of x. And y prime plus y is equal to 2 sine of x. And we're sort of at, I suppose, back here at this sort of like ansatz thing, but instead of making you guys guess, you were given the guess from the get-go. You're asked to show whether or not this thing here, sine of x minus cosine of x, is a true and genuine solution to this differential equation. Which means think back to old style classic equations. If I asked you to verify or to unverify, let's say x equals 3 is a solution to this equation, what would you do, Braylon? Plug it in. You plug it in, and then you find out if the equality holds or not. And that's exactly what we're going to do. We're going to plug in our solution, see if equality holds. If it doesn't hold, it's not a solution. If it does hold, it is a solution. Notation and professor kind of expectations for these problems differ. I'm sort of okay with having a placeholder equal sign there, as long as we're sort of understanding of the assumption that this might not be equal at the end. On the right hand side, I got 2 sine of x. And on the left hand side, I got d dx of sine of x minus cosine of x plus sine of x minus cosine of x. We'll sort of go through the motions here a little bit. We plugged in sine minus cosine into our differential equation. We got a y prime here, that means derivative. What's the derivative of sine? Cosine. What's the derivative of negative cosine? Positive sine. What's the derivative of sine? Cosine. What's the derivative of negative cosine? Or not negative, we don't, yeah, sorry, I'm bad. I'm stupid. I'm being stupid, don't worry about it. We don't have any derivatives there. I just got so used to questioning about derivatives there. We got a positive cosine, we got a negative cosine. I got cosine plus sine, hey, that's 2 sine. And it is time to answer one of the hardest questions in all of math. Are you done?
Yes.
You sure about that?
No.
So the question is whether or not this particular thing is a solution or not, which is a yes or no question, right? Either yes it is or no it isn't. So what do you think we're missing here, Diego? If this is a yes or no question, Yeah? Yeah. Yeah? Yeah. Yeah? Yeah. Yes. It is a solution.
So this over here is a differential equation. That.
Yeah.
Okay.
Right, it is an equation that involves up to the first derivative, and it's got only one independent and dependent variable. This is decidedly non-separable, though. This is first order linear. So this would be an example of a first order linear differential equation.
I have a question.
Okay.
Would it have worked because I just plugged in the y equals into that one. Did that also work?
Yeah, that's what we did.
Oh, that's what you did, but you just basically the derivative. I didn't even think to do it.
You didn't take a derivative?
I didn't take a derivative. I just plugged in the y equals into that one, and then I just solved the y prime. Like I didn't have to know the two.
So you plugged in y,
Mm-hmm.
and you solved for y prime.
Yeah. Or am I wrong?
Wouldn't you have gotten cosine minus? No. Wouldn't you have gotten cosine plus sine?
No. I got y prime equals sin x.
So how do you know that that's a solution then?
Because it equals, because I found out what y also equals, and y equals the same thing as what you gave us.
So you plugged in and subtracted.
Yeah, I found out.
And you got this. What?
No. I thought y equals sin x minus cosine. No, I plugged, okay, wait. First I turned.
I'm pretty sure if you wanted to move. No, wait, this should be y prime, right?
Yes, that's what I
Okay, so how did you get y here?
I plugged in, or I subtracted my y prime, and then I put it to the other side, so 2 sin x minus y prime, so y equals 2 sin x minus y prime. And then that's what I found as my y. And then I plugged that one into the y equals sin x minus cosine x. Yeah. And then I plugged that into that.
You plug this into
No,
this.
the y equals 2 sin x minus y prime into the y equals sin x. To the equation behind you. So that. Yeah. Would that work? Or am
I feel like you've just made a circular argument,
I like? Well,
right?
I don't understand.
Right, 'cause I feel like you started here, right, and you plugged it into here,
Yes, I went
and
in
then
a
you
circle.
worked down,
Yes.
and then you went back here, and then you saw that it satisfied that.
Yeah.
I feel like the circle has been completed.
Yes.
And circular reasoning is something that totally works every single time.
Oh, I didn't know that. I was just asking.
Circular reasoning doesn't work.
Oh, no?
No.
In this case, it did. But
I mean, circular reasoning always works because circular reasoning works because circular reasoning works because circular reasoning works. Right? If the premise of your conclusion is already assumed to be true, it doesn't matter what you're going to get a solution anyway.
Okay.
You got to take derivatives.
I have to. Okay.
Yeah.
That was just okay.
Yeah, if you were to add y prime to the other side, you end up with the original equation. It's interesting, but, yeah.
No, what I was totally expecting to hear at some point was, we did this work and then I took some derivatives. In which case I would have been like, okay, maybe that would have worked because we had to take derivatives at some point. But no, you can't circular reasoning your way out.
Okay.
What if when you got to that point where it says y prime is sine x plus cosine x, and then you took the derivative of the original one we got, so y equals sine x minus cosine x, and then you get that they're equal to each other?
Does that work for that reason?
Wait, but the zero, doesn't 5 put it 0?
Like, this is the reason why the circular reasoning doesn't quite work, and why you just plug in and take derivatives down. Because if we were to follow the circular reasoning, then this is totally fine, right? The problem is like, if I were to take this and plug it into our actual original equation here, we'd have a plus 5 here, and then we'd have a plus 5 down here, and we'd have 2 sine of x plus 5 is equal to 2 sine of x, and that's not a solution. You just plug in and take derivatives and simplify. I appreciate the ideas of trying to be clever, but you have to do that.
No, I was just like saying it.
That should be a negative 2x. Y prime plus 2y equals 2x. Nope, I'm missing 2 2's here. There needs to be a 2 here. And a 2 there. We're getting to the problems where I don't trust myself to make up problems on the fly. All right. Verify or unverify. Is this a solution or is this not a solution? come together and talk about these. Alright, let's go ahead and get started on this first one then. See the minute hand is now at 8. That was my time. So let's go ahead and find y prime. What's the derivative of 2/3 e to the x? 2/3 e to the x. And what's the derivative of e to the negative 2x? Minus 2 e to the negative 2x. All right, let's plug in all of our things. We've got 2/3 e to the x minus 2 e to the negative 2x plus 2 times 2/3 e to the x plus e to the negative 2x and question mark equals sign 2e to the x. Let's go ahead and start distributing, start doing some just algebra, symbol manipulations. So 4/3 e to the x plus 2e to the negative 2x. And we're kind of looking here for simplifying. I see that I have a negative 2 e to the negative 2x, and I have a positive 2 e to the 2x. Those are going to cancel. I have a 2/3 e to the x, and I got a 4/3 e to the x. I got some fractions to add. Do I already have common denominators? Yes. So add the tops, keep the bottom. I got 2 plus 4 is 6, divided by 3 is 2. So I got 2 e to the x. And hardest question. Hang, are we done? Is it yes or is it no? Yes? Yes, we are done, or no, we aren't done with this? Yes. Second one. Gotta tell me yes or no. There is a particular thing here that I'm going to suggest, maybe. I'm gonna sort of reimagine our differential equation here. So look like that. And furthermore, I'm going to do sort of a kind of weird variable substitution where the exponent on this new variable that I am constructing is the number of derivatives we take of our function. So traditional choices of variable substitution here is the letter R for some reason. So here I have the first derivative, so this would be R to the first power. And then here I have no derivatives, so this would be R to the 0th power, or what, like? 1. And just continue to roll with me here for a little bit. What number should I plug into R to make this equation true? -2. I'm suggesting something for later for differential equations. Right. When we're looking at this particular differential equation and we're given this thing as our proposed solution, this e to the -2x should probably make you a little nervous, because there's no e to the -2x over here on the right hand side, which means one of two things is going to happen. Either it's not a solution, that e to the -2x is going to screw everything up, or those terms generated by the derivatives of e to the -2x will magically cancel somehow, right? And it is a solution. And it turns out that at the end of this, yes, it turns out that they did actually magically cancel each other out. This is kind of why. If we sort of imagine instead of derivatives a new dummy variable and we solve that algebraic equation, we get some information about the differential equation. This is what's called the auxiliary polynomial, or the auxiliary equation. And this is the fun one, and this is the whole reason why I brought this up. We get to say that because the solution here is -2, that my original differential equation annihilates e to the -2x. In a mathematical sense, using that word, it sounds so extreme, right, Diego? Annihilation. We're just sending things to 0. So that's sort of a suggestion of something to maybe think about when it comes to the study of differential equations. Nothing that I will actually quiz you on in this class, but there is a definite relationship between a polynomial differential equation and the actual polynomial if we just stole all the coefficients. There's a real connection there. Which is why your algebra teachers, even though they might not have known why, you solve polynomials and quadratics. Yes, you're going to have to solve quadratics in the future. Get ready. It's coming back. This one. We do need y prime. What's y prime here?
1/2 square root of x.
1/2 square root of x. Keep mind the fractional exponent nature, multiply down, lower the exponent by 1. All right, let's plug in everything. We got x times 1 over 2 square root of x minus 1 over the square root of, nope, just square root of x. And it equals question mark 0. I'm going to presume that everybody got at least at this point. Is that a fair assumption, Brian? And the sort of question is what to do here. We got some fractions down here. We get to go find some common denominators. So if one of my denominators is 1, and one of my denominators is 2 root x, I want common denominators to go add those fractions. So let's go ahead and get common denominators. Multiply everything over here by 2 root x. Is that a question or you just want?
Oh no, I'm just.
All right, we get to do our fraction subtraction now. And we're here. What's x minus 2x? Negative x. And it is at this point that it is very tempting to multiply both sides by 2 times square root of x. It's very tempting to do that because we got an equal sign, right? And we're solving for x, right? Or something like that, right? This is why I keep drawing these question marks. You can't actually use that equal sign. It's kind of for the same reason as before. I've kind of manipulated that equation once we plugged in. We don't actually know or not if we have equality here. This right here is our final algebraic step. Not really a whole lot we can do to simplify from here. So you're left with the question, does negative x over 2 root x equal 0? Why do you say that? What?
You have to L'Hopital's at all?
There's no limit here.
Okay, so you're fine with saying no.
Yeah, these things are not equal to each other. You only use L'Hopital's if this is a limit problem. This is not a limit problem. Right, for this thing to be equal to each other, for this to be an identity statement, we need to have equality of both left and right side values for any number I plug into x. And if I plug in like 1 into x, I'm going to get negative 1/2. And negative 1/2 is definitely not 0. Yeah, like.
So starting with that top line, x times 1 over 2, blah, blah, blah. In order for that to equal 0, x times 1 over 2 square root of x has to equal square root of x. So you still can move that minus square root of x over to the other side.
Why?
Because
we don't know if this is equal to 0.
exactly, but
if this is equal to something other than 0, like 1, right, then as soon as we move that over because it's no longer 0 as required by our equation, we've changed fundamentally the problem. You can't use this equal sign. Remember proving trig identities? Ugh. Richard definitely does.
same with side and side and so.
Yeah. And how, like, when you're doing trig identity proofs, you draw this, like, big old vertical line where your equal sign is. and you can only work with one side of that equal sign. We're doing pretty much the same thing here. We don't know if for this y value or this y thing, we actually have equality here. We cannot assume we have equality from the outset. We need to plug into one side and only one side, work from there until we get that actual equality.
So this doesn't work.
No, you can't use that equal sign. That's why I keep drawing the question marks about the equal sign. We cannot use that equal sign. Not until we are for sure certain that this is an actual genuine solution.
Also, when x is 0, that means we have to get a y prime with x equals 0, and that's undefined.
Yeah. I'm not sure where that's coming from, but I totally agree.
Well, I mean, because he was talking about using the ball, because like you can't multiply 2x over to 0, 2 square root of x is 0, and you get negative x equals 0, but then it doesn't quite work because if y prime of x was 0, then y prime would be undefined, and it would break down the whole equality.
And like, if we could use that equal sign, right? If we could, and we wanted to prove equality here, the dumbest way of doing that would just be multiply both sides by 0. Multiplying by 0 makes everything 0, so we get 0 for 0 equals 0 real quick. And so there's all these good reasons we can't use that equal sign. You gotta just work with one side. If this was actually a true solution, we get something a little bit like these 2e to the negative 2x's over here, where we would add and subtract them and they would magically kind of cancel out. Here they did. Okay, Brandon? Gavin, how are we doing? Good. Erica, okay? Let's just do one more for today. Kind of running out of time here. Oh, I wanted to do this one. Okay, let's do 2 more. One more like this and then another one. That's different. Yes. Keep in mind this is y double prime, so this would technically be a second order linear function. is this yes or is this no?
Yes.
Yes. This is a case of, like, we take those derivatives, we plug them in, we get cancellation on the left-hand side. And here comes the one that I kind of actually really wanted to do.
Do you want it to do or you want it us?
A little bit of both, I think. I think I'll do part B here. So we got this differential equation. Kind of keep in mind it's no longer dy dx, it's dy dt. And we want to explain why these two curves are not solutions to that differential equation. And we're going to be kind of thinking about this in terms of slope again. So as I'm going through here and I'm looking at B, I can kind of imagine for a second a slope at +1, and my tangent line's kind of going up a little bit. Diego, what would you say my tangent line slope is at 1? If you had to like approximate it.
Like on Fibler's
No, like a number, right? What's the slope, right, of, excuse me, Erica. Of my tangent line there-ish. 1-ish? Yeah. All right, well, at t equals 1 and at y equals 1, right, where we were about at, if I go and plug those in up here, at y equals 1, I get 1 minus 1, which is 0, and 0 squared is 0, and then e to the t times 0 is 0. I get 0, which means at 1, my tangent line should have looked like that, right? That slope and that slope are decidedly different from each other. This thing required that I had a slope of 0 when y was equal to 1, which I don't have. Right, Diego, you said it was about 1-ish. Right, this is where I'm going to ask that you talk with your neighbors. Why isn't this a solution? You can talk louder. I feel like you just volunteered yourself, Richard.
So make sure there's 5 tables for wheels locked.
There's 4 tables there.
I know, but I'll find I'll lock its wheels.
Okay. Think Blake.
I don't think that it should turn concave down. It should just keep going up.
So your issue with this thing being a solution is there-ish? What makes you say that?
Well, as t keeps on getting positive, the slope is going to be steeper. as well as y.
Why?
Because like putting 2 for both of them.
So we're approximating this point to be at 2, 2?
Yeah.
Okay, I could buy that.
It just keeps getting bigger.
And you plugged in 2, 2 into here and it's not 0.
Yeah.
Yeah. Okay, you get e to the 2 here, we get 2 minus 1, which is 1. 1 squared is 1, we get e squared. This horizontal tangent line is definitely not e squared, right? This is definitely 0. Yeah. Approximate your points, you know, kind of plug them in. Ask yourself, do they actually match up? Is it 0? Is it not 0? The fact that we went like totally concave down here, right? That we had a horizontal tangent line tells us that this thing would need to have another kind of y minus whatever the spot is showing up. Which it doesn't.
Equation was changed to be y minus 1, y minus 2. That could be a potential.
Yeah, maybe. Right? The fact that we don't have that other factor, though, is what kind of kills it. All right. Here are your practice sheets for the day. Richard, Sophia, Pamela. Either of you guys, see Xavier before he comes on Wednesday, presumably? Hey, I'll see you on Wednesday.
We made it. Ooh. We made it.